In this video, we are going to discuss enzyme inhibitors and how they affect Landwehr work plots. First, we are going to outline what the main variables are in enzyme kinetics to help understand the Leidenweaver-Burke plot. Second, we will show what the three main types of inhibitors are and how they appear on the Leidenweaver-Burke plot. Lastly, we will compare graphs to help you identify what inhibitors may be present. So let's get started. Let's go over our variables. We can start with V, or velocity. This is the rate at which substrate becomes products. This leads us to Vmax. This is the maximum velocity obtained when all enzyme molecules are fully saturated. We also have S, or the concentration of substrate. This is how much substrate is present in a solution. Finally, we have Km, which is the substrate concentration that results in 1/2 of the maximum possible velocity. A Leidenweaver-Burke plot is known as a double reciprocal plot, which means that the y-axis is the reciprocal of our velocity, and the x-axis is the reciprocal of our substrate concentration. This allows us to view our enzyme kinetics in a linear form, which gives us two useful points. If we look at the y-intercept, we find this value is equal to 1 over our Vmax for our enzyme. If we look at our x-intercept, we find this value is equal to 1 over our Km. This is useful for our next part, looking at enzyme inhibitors. Competitive inhibition occurs when an inhibitor binds to the enzyme like the substrate would, but does not undergo any reaction. These types of inhibitors can be overcome by adding more substrate. As a result, the maximum velocity of the enzyme does not change, but the amount of substrate needed to achieve this must increase to outcompete the inhibitor. On a Leidenweaver-Burke plot, this can be seen by no change in the Vmax, but an increase in the Km. Remember that the x-axis is reciprocal, and moving closer to the origin means an increase in the Km. In non-competitive inhibition, the inhibitor binds to an allosteric site that makes it unable to bind with the substrate. This makes any enzyme bound unable to perform a reaction, but does not affect unbound enzymes in any way. Therefore, the Km remains the same as the enzyme has the same affinity for the substrate, but Vmax decreases as there are fewer functional enzymes left. Don't forget that because the y-axis is reciprocal, moving further away from the origin represents a decrease in Vmax. In uncompetitive inhibition, the inhibitor binds to the enzyme only after it is bound to the substrate. The inhibitor essentially locks the substrate into place, meaning the enzyme is unable to carry out the reaction. This decreases the Vmax as the bound enzyme is unable to carry out reactions. It also decreases Km, as less substrates are now needed to reach the decreased Vmax. Let's use this graph as practice to wrap up what we now know. We can see that compared to no inhibitor at all, our blue line has an increased Km and equal Vmax. Our green line has a decreased Vmax, but the same Km. And our red line has both a decreased Vmax and a decreased Km. You should now be able to assign what type of inhibitor is present to each of these lines compared to the basic enzyme with no inhibitor present at all.